Good afternoon, everyone. My name is Jay. I'm the data engineer at Instacart. Today, our team will show you our newly completed project, e-commerce recommendation system. This is our agenda today. Next slide. First, we will talk about the intro and the product demo and the highlight. And then we will discuss our cloud architecture design, which supports our recommendation system. Then we will dive into each component with the cloud architecture, including the data transformation, machine learning, front end. In this project, we also did some data visualization. And next, we will also talk about the data flow within the whole infrastructure. And we will also talk a little about the future work for improvement. And we will conclude it with the meet team and Q&A session. Now let's jump into the first part, introduction. I will give you a brief overview of our company background and the business problems we are facing now. Instacart is an e-commerce platform serving millions of customers every day. However, it is currently facing significant challenges. Specifically, despite having a shopping app, it has struggled to provide custom shopping experiences for customers. It has led to customer retention issues, as many competitors in the market can offer tailored experiences. Additionally, declining sales and revenue has created an urgent need to find ways to enhance business performance. In such a background, our product, the e-commerce recommendation system, was born, which was born for addressing the business issues we have mentioned. So how can our recommendation system drive business success? Next slide, please. The first highlight is that we leveraged 3 million historical user order data to develop a powerful e-commerce recommendation system. So this recommendation system can recommend products that a customer is likely to purchase while shopping. And this system is built on a scalable AWS cloud infrastructure, which can accommodate growing business demands. The last highlight is that the system can deliver highly performance and cost-efficient benefits for both companies and customers. At this point, I believe everyone is urged to see our product, and my team member Torre will have a demo now.
Yeah, sure. Thanks, Jay. Hello everyone. I'm Torre. So today I'm just going to demonstrate how our recommendation systems work in action. So yeah, what you're seeing here is the user interface we have built for other teams to easily access our recommendation engine. So this is our web application main interface. It's pretty easy and straightforward to use. What you need to do is to simply enter the user ID. So what we have now is this user ID, and then just click the button. So this request goes to our API gateway to the lambda function, which queries DynamoDB, and also do a calculation to get the top 3 recommendation based products based on the our machine learning model. So we have got our top 3 suggested products here for this specific user. So each recommendation includes product name, product ID, and also their purchase probability. So that means for this specific user, he is probably going to buy those 3 products in his next purchase. So the overall idea for this system is to make things easier for team to quickly understand what products are most likely to interest specific user, helping them to prepare marketing and sales strategies. So yeah, this is our final product. So I'm going to hand over to other teammates. They're going to walk you through our overall journey from infrastructure design, data collection, ETL pipeline, to machine model training, and how we brought all those components together to create the system. So yeah, Kevin.
All right, thank you, Terrain. So before we dive into our infra design, there's some ground rules that we need to carry out. So we have a list of rules to follow. I'm not going to read them all out, so just to save a bit of time, because we have quite a few to cover. But the important thing is that we achieve all of them in our infra design. So all right, thanks, July. Just next page, please. Okay, so without further ado, let's dive into our infrastructure. So here's the overall infra design of our system. We have several parts: the data lake part, the data transformation part, the machine learning part, the data consumption part, as well as the underlying security part, and also the CI/CD for automatic deployment. And also to mention, the entire platform is built on by CloudFormation and automatic deployments by GitHub Actions, as I just mentioned. Okay, let's start from the data lake part. So this is probably the seemingly easiest part in the entire infra design, but except for it's not. So we understand that when we're dealing with personal information, we need to be very careful of where the information goes, or who can see it, or how it's processed. So I set up a custom managed KMS key with automatic key rotation for each of the buckets, block all the public access for each bucket as well, enable version control, enable object lock for compliance. And also, for me to better manage the infra, the access log has been saved in the log bucket. And for minimizing the cost, all buckets have their lifecycle rules enabled as well. And in terms of the functions of the buckets, that's from the top left. As their names imply, the raw bucket zone is the raw zone bucket, is for storing the raw unprocessed data that we're given from someone. And the clean zone bucket is to store the clean and normalized data by the first ETL job. And the curated zone bucket is to store the data that's been fine-tuned and machine learning ready, and it's from the second ETL job. And last but not least, the consumption zone bucket. This is to store the artifacts and the outputs of from SageMaker, and to be ready to be extracted to a DynamoDB table for data consumption. And then we're going to jump into the data pipeline part. So it consists of the ETL section and the machine learning section, and also the visualization section. I just put that in there because it's a fairly small section. So basically, we use Glue workflow to orchestrate what we have in Glue, which includes 2 ETL jobs and 2 Glue triggers. So the idea is that we use a Lambda to monitor if there's any object level updates that's been going on in the raw bucket. If there is, then the first ETL job is triggered. And when the first ETL job is done and sends a signal to the Glue trigger, it triggers the second ETL job. And then we have another notification Lambda to trigger the SageMaker instance. So that instance is for batch prediction. And this happens when the curated bucket is being updated. Similar idea with the raw bucket as well. So we also have another Lambda that provisions a SageMaker Spot instance to train our model. And we've set it to be triggered once every month using an event bridge cron job. I forgot what the exact name of it. Probably it's not a cron job, but it's something else with cron. And then we come to the visualization part. So we use Tableau for visualization, and Tableau is connected to Athena, and then the DAs can query things and make dashboards from there. And also to mention how we make sure of these of the security of the data pipeline. So we have a KMS key for Glue. We also collect metrics and logs to CloudWatch and CloudTrail. SageMaker instances are being deployed in a private subnet within the VPC. And also we set up private security groups, VPC endpoint, NAT gateway, so on and so forth, just to secure, just to make sure that the data or the traffic is secure. And also to use the Spot instance to save more money. And also for the VPC endpoint, it's not only does it save money, but it also makes the traffic stay in private and not be exposed to the public. So it's going to be more secure and also faster because it's a straightforward line from S3 to outside the VPC. Right, and the next part is our data consumption part. So this part we use DynamoDB, API Gateway, and S3 bucket for static website hosting, and also CloudFront, Route 53, ACM, and also a WAF as well. So they're used for the website as well. And this part is quite straightforward. So I mean, the data is from the consumption zone bucket, and the data is being ingested into a DynamoDB table, and then the front end website can read data from the DynamoDB table using API, and the API is managed in API Gateway. And the WAF is just to avoid malicious requests, such as a DDoS attack, for example. And something more is that the website has been certified by ACM, and it's being globally distributed by CloudFront. Okay, so all right, now so we're at the CI/CD part. So I've made two pipelines. One is to deploy infra and the script, and the other one's on the right is to deploy the front end website. To be honest, I should have split the first pipeline to two, but really didn't have the time to do it. July is going to mention that a bit later. So, but basically the first infra pipeline is to first check out Git and then authenticate, then create S3 template buckets for the scripts for IAC, for ETL, for Lambda, and also for SageMaker. And then it validates the IAC code, and then deploy IAC to AWS. And finally, to clean the workspace after everything is done. And the front end pipeline on the right, it just simply does deploy the React app to the S3 bucket. And that's pretty much it. And the pipelines are set to be triggered automatically by commit to GitHub. So one thing is, I'll say something about security is that it's instead of using a conventional access key, secret key to access AWS, I created a OIDC role in AWS and use OIDC role to authenticate GitHub. So this gives a shorter duration of the token just to increase security. All right, now we're finally at the last part of my infra setup. It's the security part. So apart from what I mentioned earlier, also implemented RBAC for our team. So we have an admin role, a DE role, and a DA role. So I'm the only one in the admin role, as you can see. Well, anyway, I probably can't see that over there, but yeah, so I'm the only one in admin role. And all of us is in DE role, and the members who are doing the visualization part is in the DA role. Seems to be quite a generic roles, but it's because probably our team is smaller than most teams. But when the team is getting bigger, then those roles are going to be more useful. And what else? So, and also for service roles, we also use the least privilege rule. So this is one of the examples that I play out. So we actually spend a lot of time on this, and it's quite hard to find the best permissions within a short period of time. I don't think we can actually do that even we have enough time at all. But yeah, so we understand the importance of the security of the system, so we don't regret the time we put in on this. And also to mention, the root account is never being used, and we try to avoid using it. And to be honest, we don't really need it anyway. And our account have activated MFA for all of our users as well, just to make sure that yeah, it's not, nothing's can be compromised, hopefully. Okay, I think, and on the right-hand side, that's the summary of the security part that I've implemented to the IAC, to the infrastructure. And yeah, I think that's pretty much what I need to cover. So now Ivan's going to start with the data pipeline part. Thank you.
Okay, so thanks, Kevin. Hi guys, I'm Ivan. So in the next couple of minutes, I will introduce more detailed stuff on doing ETL jobs in our data pipeline. So first, let's talk about why we've chosen AWS Glue for our ETL needs. So firstly, AWS Glue is a game changer because it provides a serverless environment for running our ETL jobs in the cloud. So say goodbye to the headache of manually configuring clusters, like what we do in Amazon EMR. And I know EMR with several EC2 instances is really overwhelming. So basically with AWS Glue, we can focus on what really matters. So just on building our ETL workflows, no infrastructure. Now let's talk about performance. AWS Glue use Apache Spark, which help us process our data quickly. EMR does offer different tools like Hive and Presto for handling big data like streaming data. But for what we need right now, Glue is perfect for managing our batch data. Another big plus is that Glue automatically scales with our workload. This means we don't have to manually adjust anything. It just works smoothly as we need it. And here's the best part. Glue works on pay-as-you-go. We only pay for the resources we use while our jobs are running. This makes it a smart choice for saving the cost. So to sum it up, Glue is easy to use, perform well, scale automatically, and help us save money. Now let's talk about how Glue works for our ETL jobs. We use a few key services provided by Glue, which are ETL jobs, Glue triggers, and Glue workflows. So here's how it all comes together. First, we use Glue workflow to manage the entire Glue ETL process. When batch data comes in, it will be saved in our S3 role zone. Then a lambda trigger function will be triggered to start the Glue workflow. Once the workflow starts, the first Glue trigger runs on our first ETL job, which cleans and validates the raw data for further processing. The clean data is then saved in the clean zone. Once the first ETL job is successfully finished, the second Glue trigger starts the second ETL job. This job focuses on transforming the clean data and doing feature engineering. The results of this job are saved in the QA zone for later analysis, reporting, feature engineering, and machine learning. Now let's look at the diagram that shows how the data is stored in our S3 buckets. In the row zone, we have 5 folders on the data folder, representing our batch or historical data. After the first ETL job, which involves cleaning and validating the data, we save it with same structure in the clean zone. In this zone, we also create a invalid data folder to manage any data that didn't pass validation. Next, the clean data is transformed into more useful formats. The curate zone contains folder like OPO prior, which is a large data table joined from the order and order products table. This table is commonly used by both data engineer and data analysis team, so we save it in S3 bucket for easy access. We also store user features, product features, and user product features, which are important for analysis. So we combine these useful information with our training and testing data, saving the results in the machine learning data set folder. This data is separated into training and test sets, making it easier for the machine learning team to use efficiently. And then I will hand over to Jay for more detailed explanation on ETL jobs.
Thank you, Evan. Since everyone is familiar with the Glue architecture now, I will explain the detailed ETL processes. So I will break down this process into 2 parts: data cleaning and feature engineering. So when we clean the data, we mainly consider the 4 aspects. The first one is dealing with the missing values. When we check the data quality, what we have found is that the DCC supply ordered column in the orders table has some missing values. So after discussion, we think this information is very important because it can represent very useful user behaviors. So we decided to set it to -1. We don't want to set it to 0 because we want to distinguish it with the scenario when a user may have 2 or more orders in the same day. And we don't also want to set to remove these missing values because, as I said, these are very important information. And the second aspect we considered is duplicates. And the next one is normalization. So basically, we normalized our data to ensure the values in each column can align with the data schemas that we have designed. And the last aspect is the invalid values. Specifically, we performed the cross-table validation to ensure that our data has a high quality because it will affect the model training performance. And when the our data is clean, we started to perform the feature engineering. So in this section, we mainly did 4 things. So the first one is we created useful new features because we wanted to use these features for our machine learning model training. So these new features included can be categorized into 3 categories, including the user features, product features, and user product interaction features. And I will explain the detailed features in the following data flow part. And the second thing we did in this part is we performed the correlation analysis because we wanted to analyze the correlation among the different variables. And when 2 variables is correlated, we wanted to keep only 1 because this means these 2 variables represent the same information. And we also tried to convert categorical variables using one-hot encoding. But when we did this, actually, because using one-hot encoding will include or introduce new columns in our data set, and will enlarge our data set. And when we're training our machine learning models or SageMaker, the training process will crash. So yeah, so this is the one issue we got in our project. So after discussion, we decided to not to consider this step in this stage. Actually, I wanted to discuss this with our project supervisor. I mean, we wanted to ask you for some advice regarding this issue. And the last part is scaling variables, which means that we want to avoid some features are dominant when we're training our machine learning models. So the final output of our ETL process is 2 data sets, which are ready for our machine learning use purpose. So they are training set and data set. And you can see our training data includes 8.4 million records. And the test data includes about 4.8 records. And both of each are with 35 features. Of course, they are included both the dependent variables and target variables. Due to the time limit, I can't go into every detail regarding this process. So if you are interested, you can access the detailed process by this link. Next slide, please. And in the ETL processes, we also did some exploration. So the first exploration we did is we considered the slowly changing dimension in the data story or loading stage. Because we wanted to introduce data streaming for our project in the future. So when the new data comes in, we wanted to keep all the previous and new data. So as it said, we deployed SCD type 2 in this case. But in this step, we also got the same issue that I mentioned before, and because this step will introduce the more columns in our data set, and it will also will affect our model training processes. So we didn't consider it in this stage. And another exploration we did is partitioning for the benefit of efficiency. But after discussing or have a consultation with our project supervisor, Jerry, he suggested that our dataset is not enlarged in this project, so maybe this step is not that necessary. So this is some evidence of the detail of our detailed exploration. So that's pretty much about the ETL processes, and I will head over to my team member Sean to explain the machine learning part.
Okay. Hello everyone. I'm Sean. In the earlier stages of project development, we focused on solving the problem of local debugging of the model and manage all of our code in Git. With zero-cost local debugging, we were able to quickly adjust and verify the model and provide feedback to ETL. We then achieved automated and scalable development through AWS, which ensured the stability and the repeatability of the model in a controlled environment. Next page, please. As for the model between XGBoost and the graph-based model, we found that XGBoost performance outstanding when processing tabular data. With the characteristics of rapid development, strong recommendation performance, and easy development, while graph-based models are more suitable for graph-based data analysis and has certain advantages in large-scale recommendations. We also designed a heterogeneous graph model to handle the multiple type relationships between users and products, which can effectively capture the complex correlation structure in the data. After a comprehensive analysis, we decided to use XGBoost as the recommendation model for this project. Next page, please. We successfully deployed 2 models locally. For XGBoost, we can evaluate the model performance from multiple evaluation indicators such as precision, recall, F1 score, and accuracy. For GraphSearch, the evaluation indicators can only be analyzed from the loss, cosine similarity, and R-square, which are less interpretable and intuitive. However, for product recommendations, they can be obtained directly through the user IDs, which is more convenient and faster. I will hand it over to Zibo. Thank you.
Thank you, Sean. For our model training and inference architecture, we use ETL resource stored in Curtis zone as input. When there is a file loaded or updated in the corresponding bucket, a lambda function will trigger the training procedure. After the completion of training, the model will be saved in consumption zone for the batch inference in the future. Specifically, file changes in test folder will trigger batch inference, and the train folder will trigger another one, the train instance. The reason we designed it in this way is that our recommendation model is not very sensitive to time. We do not need to train it again and again. Considering the cost, the largest site we choose is batch transform strategy. Which means we use our model to do all the predictions we need together to make the necessary result prepare for our stakeholders instead of predict it in real time. Moreover, we choose DynamoDB as our final storage place for batch transform results. Compared to other methods, it is easy to set up, and it could be searched through key value, such as user ID with low latency, which is suitable to our user scenario. Next, please. For the training process, we can monitor the performance inside the instance. Also, as we use the XGBoost as a logistic regression model, we could not use a metrics summary directly. So we set a threshold value to determine whether a product should be recommended or not. By treating the recommendation decision as the predicted target, and to compare it with a reorder label as the ground truth. We can then calculate the precision required and the similar stuff to evaluate our model properly. From the pictures in the right side, you can see that the probability distribution of data with different labels, and also the changes of precision and recall through different threshold value. To keep it balanced between these metrics, especially for the F1 score, we choose 0.3 as our threshold, and the corresponding metric summary is shown at the bottom in the left side. So we can see the model is performed better for the label 0, which is acceptable since data with label 0 occupied most of our data set. And our accuracy is at 90%, and the weighted F1 is also near to it. Next, please. After we successfully run the training and batch transform procedure, the models and the transform jobs are listed in the SageMaker, as we can see in the left side. Each time we finish training, the endpoint will be deleted since we choose batch inference strategy as mentioned. So we do not need to predict in real time. Eventually, our model results are uploaded to DynamoDB to support frontend. We can use user ID as partition key and product name as sort key, and also the corresponding probability as the body for the need of sorting the recommendations. Thank you. Now I would like to hand it over to Torin for the front-end part.
Thank you, Tor. So yeah, as we just mentioned, all the data gonna be stored in the DynamoDB for the front-end use purpose. So I'm just going to dive into a little bit deeper why we choose DynamoDB instead of S3 or other databases. So there are a few reasons. The first one is automatic scaling. So the DynamoDB can handle various sorts of user requests seamlessly. It automatically scales up or down based on the traffic. So this is gonna ensure our system remains responsible regardless of the number of concurrent users. The second one is the cost effective. So DynamoDB has pay-as-you-go model, which means we only pay for actual usage, which is quite good for the company because you can minimize the cost. Performance was also very important. It delivers millisecond response time, making our system instant and keeping user engaged. Additionally, its serverless architecture pairs perfectly with our API gateway setup. So those are pretty much the reasons we decided to go with DynamoDB. And from the DynamoDB to our front end, we have also implemented API gateway to connect them and a lambdafunction to query the database to do a simple calculation based on the probability to get the top 3 products for the user. So for the API gateway implementation, we have focused on 2 methods. So the first one is get method. So this is basically just to retrieve the data from the DynamoDB. And the second one is called option method. So this is to handle CORS request, ensuring a smooth cross origin communication so that our front-end website page can talk to the backend and then get the data out of the backend and also display on the front-end page. To process those APIs, we also have a lambdafunction between them. So the lambdafunction is going to process all requests coming from the API gateway and then query the query in the DynamoDB and also do a little bit of calculation to get the top 3 products based on the data we get out from the DynamoDB. And then finally return the result to the front end. So moving to our front end implementation, we have decided to use React.js as our framework, giving us the power to create a dynamic and interactive user interface. Also used CSS for responsive design, making sure our application looks and works great on any devices. So that's pretty much all about how we, from database selection to API implementation in our final product. I'm going to hand over to my teammate July, who will demonstrate how we do the data visualization using Tableau.
Hello, everyone. Can you hear me? All good? All right. So thank you very much, Ture. Now I'm going to demonstrate how our infrastructure served our second group of users, the data analysts. As you can see in the left, it's our infra diagram for our data analysis sandbox. We used S3 clean zone as data storage. We built a database in the Glue data catalog for analysis purposes and use it for cataloging and metadata management. Data analysts could then use Athena to query the data in the data catalog and also create views. We used the Tableau as our visualization tool and connected it to Athena to access data. Here is a small demo of how what it looks like. So on the left, it's our AWS Athena console for data analysts, and you can notice the database in the catalog and also the view data analyst created. And on the right, it's our Tableau UI. After connecting to Athena by using AWS Access Key and Secret Key ID, data analysts are going to be able to access all the data and also the views to create dashboards. Here is an example we created using our project datasets. And when choosing live connection, the dashboards will be updated simultaneously as well. And next, I'm going to explain some of the key features of our sandbox. First, isolation. Any transformations or aggregations are performed on copies of the data, not the raw or the production datasets. In our case, data analysts are not granted with permissions to change data in the original S3 bucket. This makes sure data analyst activities do not interfere with the production system. Second, flexibility. Our design provided data analysts with freedom to query, transform, and analyze, and creating views, selecting and creating features they need frequently without any restrictions. Furthermore, tools and data in this sandbox is highly accessible for our data analysts. We use mostly tools native to AWS, and the connection could be easily configured using AWS credentials as well. With regard to security and governance, in our project, we enforce the fine-grained access control to data analysts by creating dedicated Athena work group and databases for DA role, and also grant write permissions only to the landing bucket, so not the original one, the Athena query result one. And we don't have personal sensitive information we need to mask in our project. But if we do in the future, this could be easily managed before loading the data into the data catalog as well. And this is the end of my part. And now I'm going to hand over the presentation to Liu Jie, who will go through our data schema flowchart.
Yeah, thank you, July. And our team has introduced our designed infrastructure, and now I will explain the whole data flow within the infrastructure so everyone can have a better understanding of the whole system or our designed architecture. So first, in the S3 raw zone, we got 6 tables that are provided by our project supervisor. And if you, I believe you guys can remember, we mentioned 2 glue jobs in our ETL processes. So when the first glue job starts, our data will flow to the clean zone. Because in this process, it will change the data structure. So the tables will remain the same, but the values or the formats will change because we have already done some data cleaning in this process. And then when the second glue job starts, our data will flow to the curated zone, S3 curated zone. So as you can see, we basically got 5 tables, including the user features, product features, user product interaction features, and the 2 machine learning data sets, including the training set and the test set that I have already mentioned. And when we train our models, our data will flow to the consumption zoo. So in the consumption zoo, you can say there are 2 data sets. They are training set and test set. And when we finish training our models and we stored our prediction result to the DynamoDB, so our data will flow to the DynamoDB. Yeah, move a little. To the DynamoDB. So in the DynamoDB, we got 1 table. Prediction tables will store our prediction results, which is included user ID, product name, and predict accuracies. So this is basically about the data flow within the infrastructure. And next, I will head over back to my team member July to explain the future work.
Thank you so much, Jie. Now I'm going to talk about some areas for future improvements. First, let's focus on the infrastructure. We could enhance our design for scalability, testing it for increasing workload and incremental data, because we haven't got the time to test it yet. We should also consider its fault tolerance. With our highly automated pipeline, as mentioned before, how could we handle errors and initiate retries? Next, let's look at our infrastructure as code. Considering CI/CD, as Kevin mentioned before, we could separate the development from script commit in our IAC to enhance flexibility and control over developments and reduce risk of unintentional changes. Also, for our current cloud formation, our modules for Glue, ETL, and SageMaker are too large. We could break them down into smaller modules to increase reusability. Another important aspect is, of course, security. At the moment, we have already implemented business-level fine-grained access control for different accounts, but could still reinforce the least privilege rules in some areas. We should also set up backups of infra and our data in another availability zone for disaster recovery. And last but not least, considering other use cases, we could also simulate the case when data source is from a data warehouse in a private subnet, which is common in business, also considering simulating streaming data in the future. And now let's meet our team. Our team leader is Kevin. And we also have other teammates, Terrain, and this is me, July, Liu Jie, Ivan, Zibo, and Sean. And our supervisor is Leo and Jevi. And I want to thank our supervisor, Leo and Jevi, for all the support that we received, representing all of our teammates. And I want to thank all our teammates for the great effort and teamwork that we have demonstrated during this process. And thank you very much. And now it's time for Q&A.